Okay, so I think for today's class, my plan is just to get some introduction for chapter 14, partial derivative, just a little bit. And I will add maybe some exercise to help you. Yeah, Wednesday. Do you prefer Wednesday or Thursday? Thursday? Better Thursday? Okay. So I think next week, Wednesday class, we can have, exercise. Okay. So now we move to another section, which is the partial derivative. So I'm skipping chapter 13, and I will make the chapter 13 as supplementary. So it will not include in your exam, but you need to at least see the content, okay? Especially for chapter 13, for factor functions. I think the important thing on those chapter, because it's I think quite short, the chapter, but the way we have, for example, chapter 12 we learn factors, right? We learn factors, some geometric spaces, 3D factors, dot product, cross product, that I hope you still remember how to use it, and also how to represent the vectors by taking some equation of a line or plane. And by those factors, we can represent function in terms of factors, which we call the factor functions, which we are going to use frequently in chapter 14, the partial derivative. So I hope you're already familiar with the factors, okay? And basically what the factor functions as a consequences are, basically you are going to have three different axes, right? X, Y, Z. We have three different directions at least. That means for every part of the factors, we can first derive or we can integrate, and all the property that we already learned in calculus, we can also apply on each part of the factors. Okay, so for example, we have the factors that's represented by I, J, K, or even within the different factors like this one, for example. We can represent factors like this, or we can represent, like, for example, A, I plus B, J plus C, K. Okay. So basically what we have here is every terms we can differentiate, we can integrate, and other things that is at least you need to read out is about the curvature. The curvature is telling you how smooth the curve is. Okay? So I hope I can pack all that information into one video that you need to at least, maybe I will record it and you need to at least watch, okay, as a supplementary. Okay? It is not really directly included in the exam, but the knowledge of those factor functions you need to know beforehand. Okay? At least that will be my plan for you. Okay. So let's get into the partial derivatives. Okay. So partial derivative, we start with the functions of two variables. Okay, let's start with function of two variables. For example, we set some temperature, okay, so some temperature functions on this Earth's surface, So imagine you have, let's say this is the Earth surface, which we can relate the Earth surface with the positions, x, y positions, right? So we have x, y positions, like for example here, P, we have x, y, okay? And in the temperature, of course, not every area will be having the same temperature. So we could, let's say in here is going to be hot, and then maybe this part is going to be not really, and maybe in between, there's something in between, okay? So we can set some function, let's say T for temperature, as a function of two variable x, y. So we can set up points, like maybe if we move our points, then we can see perhaps the temperature will change according to the function. But generally, we usually use z equal f x, y. Okay. So this is the differences between calculus 1 and calculus 2. Calculus 1 we deal with, so let me write here. So calculus 1 we deal with y equal f of x. In calculus 2 now we deal with at least two variables, at least two or more. Okay? Two or more. It can be 3, 4. Okay? And the core or the important part within the semester, calculus 2 is about this chapter and multiple integrals, okay? Because that is defining how we are going to be able to use the techniques, how to partially derive, and also for some, if we have multiple integrations. So let's see the definition here. This is example that we can have. Actually, this is having three dimensions, but we are seeing from the top. Okay? And we can see that every part of this point, it will relate to the z-axis. So the z is actually here. Okay? So we put z here to see that it's all connected. Okay? So every point has a connection with different z value, as z is a function of x, y. Okay? So we could say that the function of two variables assign that each ordered pair for this x, y axis and some set of, we call this is D, some sort of actual domain, okay? We could say that's domain, and denoted by the function. And we call it D is the domain of f, and its range is set value of f, that is this. Okay? You don't need to write like the whole sentences, just a few keywords like the functions, domain, okay? I think just that. Okay, so the xy, now we have two independent variable. This is independent variable, and z is the dependent variable. Okay, and then I will go directly to the practical use for the graph. Okay, Now, of course, if we have some set of f that is on domain D, then all the set x, y, z in the three dimension such that z is function of x, y, and x, y is on the domain, then we could say, and we could represent those in this illustration, which means that if we are going to set some points in D, okay, it will also connecting to the value of z, because z is a function of this x, y. So every point we move the point on the domain, as a consequence, the point on this surface here will also change. Which means we are going to see some surfaces, okay, that have different, like you can imagine like a mountain, okay, mountain, if you are maybe taking some classes in your maybe junior high or maybe high school. If you're taking class on geography, like geographical lesson.
Geography.
Yes, geography. So you have maps, and there are several maps, right, that maybe different colors mean different heights. And that is actually one way to use the function of two variables. Right? So maybe the different height is represented by the z. Okay? So you can see like this is like a mountain. Like it's like, maybe it's like having a mountain like this. And maybe we can have like more and more like that. Okay, so it's kind of like it has like different z. So every changes in x1, you can see the height differences. Okay, so this is actually what that is. Okay? So we can have we say that this is the surface. Okay? This is the surface. Okay, I think we can set up to the next one. Okay, now this is the example. Okay, the example, of course, with some sort of really interesting function, but I would like you to focus on what can we do from here. Okay. So you'll see that because we now looking at 3 dimension. But the goal or the set in calculus is practically similar. For example, we have something at this point here, which we call the maximum, right? The maximum point, or we say the local max, and the below, maybe that's some below here is the minimum point here. Okay, and there is also one subject in the chapter 14. We are going to find the maximum minimum value. And as I mentioned, we may also consider a point that is not minimum, not maximum. That is actually, we call the saddle point, like the last discussion, the saddle point. Okay. So there's some example. We call this the counter, okay, the level maps like this one. Okay. So this is we called the level curves or contour. So level curves or contour is basically, we say that the function of 2 variables will be equal to k. K is a constant. And of course, we need to make sure that k is also in the range of f. So you will see that if we change some value of k, you will see that it's also related to the tracing of the surface, how the surface looks like. Okay, this is just introduction. Now I think we can, and the same way, if we add like more variable, For example, we can write three variable f x y z. It's also possible, but the more variable we add, the more difficult we are going to visualize the graph. Sometimes we can still visualize the three variables because we can make one variable to be fixed. But if we take more, it will be a little bit difficult to visualize. Because we are living in a three-dimensional space, which are not really easy if we have like more dimension in our life. Okay, I think I will just skip and then go through the introduction of the limit and continuity in this two variable. Okay, so let's see this two. So let's start from here. Okay, let's start from, let me check first. Okay, so in calculus 1, let me just redraw. We have, let's say this is a random f of x. Okay. And then suppose that we set some point here. Let's say this is x0, y0. Okay, so this is x0. And we would like to know when we take the limit, as x approaching, let's say the x0. This is sometimes we would like to evaluate, like in calculus 1, right? And how to evaluate this? We can evaluate by taking the left hand limit or the right hand limit. Okay? So we can take that each like that, and then we need to make sure that this is equal with the left hand limit. Suppose that we have some L. Okay? So we say that if these two equal, then the limit of f of x is equal L. Okay? And of course we need to assume that limits should exist here. Okay, now if we, let's say, taking this point here exactly at that point, exactly at this point, that there's some removable point here, discontinuity, and we take the limit. The value or the evaluations should be still the same. Okay? Because we are using limit only when we are getting really close, or the delta is really small. Okay? Small changes that we can ignore it. Okay? So limit is a technique or the tools to ignore that small changes. So even though there is a hole, we still say the limit is equal L. Or maybe let me write here, this is L here. This is L. So this is L. Okay. But for continuity means, so this is limit exists, okay? But for continuity, we have the limit, but we need to also evaluate on that point. Okay. So this means continuity. Okay? This means continuity. So the limit value should be equal to the function when we pass the x0 inside. We plug in x0. Okay? And we say, if that happens, we have continuous functions, right? Okay. These are the limited review of calculus 1. But here we have whole. And at this point, it's undefined, right? The function undefined. So we say when we have this, it's not continuous. So we need to make sure that if you want to make it continuous, we need to have this. Okay, now, using the same logic, same reason, we are going to move this 2 dimension into 3 dimensions. Okay? It's a little bit complicated, but hopefully I can give you some introduction. Okay. So this is for next explanation. Let me explain in more simple graph. Okay. So let's say we have z, x, and y. And let's say we have some surface here. Okay. And this is going to be, let's say this is the point. Maybe green. This is the point x0, y0, z0. Okay. And let's say this is going to be up that point. So this is y0. This is the x0. So if we take limit, so let's say the surface here is basically our function f(x,y). So let's say we are taking limit of f(xy) as xy will be getting closer to x0, y0. Maybe let me write a little bit to the right side, go there. Okay. So imagine we are going to approach this point here. This point here. So we would like to approach this point. Okay. If we see from the top what we have done in calculus 1, we can approach x0 from the right, from the left, because we only have those 2 options, left, right. And now we are enlarging our spaces. How can we get closer to this? How? Any idea? Because you see, like, imagine, okay, this point here, okay? This is 3 dimensions, right? Okay, I want to get close to this table. I can walk from here. I can walk from here. You can also walk from there, right? So, infinitely. From any possible way, we can have infinite many ways, right? Got it? So, we're going to write here. There are infinitely many ways, or in this case, the curves, okay, curves that approach the point x0, y0. Or to be precise, the point on the surface at z0. So how do we take this and then apply it to our limit? So I think the best way, if we can provide some some curves. Okay? So we need to, like for example, the way I'm walking through this and up here until here, I can make another curve. Right? For example, I can write maybe y equal x like this. And then imagine that y equal x through that path. Can I get through the point? Or maybe we have another one, like maybe the quadratic function x with y equal x squared. Can we have y equal x squared and then try to get into this point? So we can have several like examples that we can try. Or maybe we could try when x equals 0, like line, just a normal line, or y equals 0, that is simple number that could make easy to observe. Okay. Let me show you as an example to get so that you can, I think, get some understanding. So for example, if I have limit xy getting closer to 2, 1, let's say the function is negative xy over x squared plus y squared. Okay. So remember, in limit, every time you have limit, the first thing you can do is just test the limit. Okay? Check the limit. What will happen? I think there is no problem, right? If we put x1 inside this function, no problem. We can see the numbers, right? So we can put the numbers. So negative 2 over 4 plus 1, right? So we have negative 2 over 5. Okay, we have this limit. Now the problem arises when we approach 0, 0. So if we look now, if we plug in 0, 0 to the system, we are going to see some 0 over 0 situation, which in calculus 1 we call these terms as indeterminate forms. But for now, for this function of two variables, the 0, 0, we can imagine, so imagine, let me write here, so imagine there are several ways to get close to 0, 0. For example, to get 0, 0, we could set fixed point. Let's say we can say y equals 0 and then only x are moving. Or set some x equals 0 and then we think, okay, we are going to move through only y. But when x equals 0, so only on this axis, okay, only on each axis. So we could try that as well, okay? And then we can still see that they will also approaching, at least they're trying approaching the 0, 0. Okay? So we can take the limit along x-axis, which y is equal 0. So limit xy getting 0, 0. What's happened is we are going to take y equals 0, and it means that this y here and y squared will be 0. So we could see that this will be equal to 0 over x squared plus 0. Okay, this is also limit And then we see that because this is going to be 0 first, okay, before we add 0 from the limit, this is already 0, okay. So we can say that when y equals 0, the whole limit becomes 0, okay. This will become 0, okay. And then we try another axis. So we can say that we take the limit along y-axis. The same way we try to make and now x equals 0, so the top equation will be 0 and then the bottom one will be 0 plus y squared. With the same reason, this is also 0, right? This is also 0. Because we make the constant 0, okay? So if we just look at these two conclusions, that they have the same value 0, we may think that this limit will exist, right? This limit will exist because remember in calculus 1, left-hand limit equal right-hand limit. But now there are many ways, right? So we need to choose wisely which one that makes this limit maybe not exist. So the easiest one is taking the x-axis or y-axis, or one other method is taking when the y equal x, okay? So limit along y equal x curve, okay? So we could take this limit and then we write this. So we can exchange y with x or x with y. Let me change to all with x. So this will be negative x squared over 2x squared, okay? So you can see that we can cancel this part, which gives you negative 1 over 2. Which this is not equal to 0, right? Not equal to 0. That means by taking this y equal x as our path to get close to the point, it means that we prove that it is not equal, which means that limit does not exist. So we can write limit doesn't exist. So to be exist, all the possibility need to be taken care of. Okay, so that's how we can approach a point in 3 dimensions. Okay, so in 2 dimensions we only can move left, right? But 3 dimensions we can move anywhere. Right? Okay. So we can make our own curve. We can make line. We can make maybe some polynomials. Okay. And to check or to test the limit, my suggestion is trying to have a simple path, simple curve, okay? Like y equal x, or maybe later you will see from the, I think it depends also on the structure. Sometimes if you think maybe we need to check y equal x squared or x cubed, maybe that will help to solve this limit. it depends on the function. So you can have this path, any curve, okay, any curve that's possible, any curve that's possible. Okay. Anyway, the definition now, we can make a definition here. Okay, it's including the epsilon delta definition. So the f is a function of two variables, which within the domain it include point that is close to AB. So AB is the one that we want to evaluate. So close to AB, and we say the limit of fxy as xy approaching AB is equal to L. Okay? Which assume that it is going to be exist. Okay? And the limit can also represent by epsilon and delta, which they are also, remember the epsilon delta? The epsilon in calculus 1 is for y, right? For y. So we take some delta, and then it will it will affect the epsilon. The delta here, you will see that it has square root and then x minus a squared plus y minus b squared. This is the distance in 3 dimensions. In calculus 1, we just set absolute value, maybe x minus a, absolute value less than delta. Now we have the distance because we have 3-dimension space. Okay? The distance in 3 dimension. So this is distance in 3 dimension. Okay. So this is just to confirm that we will have some epsilon every time we choose some delta. Okay. Delta and epsilon are actually the small changes that we ignore in the limit concept, because in the true definition of limit, we want to make sure that if we say the small changes is really, really small, how small it is, then we define the smallness in terms of delta and epsilon. Okay. Okay. This is how it looks like. So we say that this is the small changes in delta. So delta is in the distance, okay, distance within the xy domain, okay? And then it will affect the z-axis as in the epsilon. It can be plus minus epsilon. You will see that we will have this, the delta, and this will be the L plus epsilon or L minus epsilon. And imagine that this shape here is going to be really small. Okay? It's going to be really small. So what we are doing on this example before is actually we're trying to make this. Okay? So if fxy, and then we have L1, that's the path, the curve path we choose. Okay? And then, the path curve is C, L is the value. Okay, the value. So if f getting closer to some value L1, as the xy getting closer to the point, okay, along this curve, okay, C1 is the curve. And then we have L2 also. It's also along some curve. Okay? If they are not equal, then limit doesn't exist. That's practically what we have before, the example. So if they have different value, then we say the limit doesn't exist. Okay? So we could try one more example. Limit So I think if you just checking through the x-axis and then y-axis, I think you could see that if this is 0, this will be -1. Right? If this is 0, this will be 1. So already different, right? Already different. So we can say that this also doesn't exist. Okay. So we set the path is when x equals 0, which gives you this is going to be 0 minus y squared and 0 plus y squared, which give you the -1. Okay, and then we can take another path, which is y equals 0. And then this is going to be x squared minus 0 plus 0. So this is going to be 1. So because this is not equal, we can write, since f has two different limit value as xy approaching 0, 0 along two curves, limit is or doesn't, or maybe let me write, then limit doesn't exist. Okay, I think I will just end up until here. Okay. Okay. Any questions so far?